Okay, so objective-driven AI. So for those of you who were at my talk last year, this is going to be sort of progress in the direction that I indicated last year, and a bit more background information. Okay, so really what we need is build systems that essentially can reach human level AI, systems that can learn, they can remember, they can reason, they can plan, they have common sense, and as well as are steerable and safe. And currently, generative AI systems, or the current breed of AI systems that we have at the moment, are not able to do pretty much any of that. So, so how do we get there? Mohammed tells me that my camera is off. Is that the case? You guys can see me somehow? Oh, here we go. All right, now you can see me, right? Hopefully. Okay, so first thing is machine learning really sucks when we compare it to what humans and animals can do. Of course, a lot of success of machine learning has been through supervised learning. Reinforcement learning really only works for games or virtual environments. You need to use all kinds of other types of learning if you want it to work in the real world. And what really has revolutionized machine learning in the last 5-6 years is self-supervised learning. And generative AI is just uses self-supervised learning, but it's not the only way to use self-supervised learning. So animals and humans can learn new tasks very quickly. They can understand the world, how the world works. They can reason and plan. They have common sense. And their behavior is driven by objectives, right? We set goals for ourselves, and then we figure out how to achieve those goals. And so the question is, do we actually need to work on human level AI? Like, is it a worthy pursuit? And the answer is yes, because there is a future in which basically all of our interaction with the digital world will be mediated by AI assistants. We're not going to be going to, search engines and whatever. We're still going to be going to social networks because that's communicating with other humans. But when it comes to communicating with digital content, we're basically going to be going through our AI assistants. We're going to be asking them questions, and they'll be answering. They'll be helping us in our everyday life, and that's an AI complete problem. Those systems will need to have basically human level intelligence if we want them to be non-frustrating to use. So it's a scientific pursuit, a technological challenge, but also there is real product that we need to develop that have human level AI. We're nowhere near human level AI today. Like, despite what you might hear or infer from impressive demos of generative AI, among other things, we're nowhere near reaching human level AI. If we were, then we would have machines that can learn to drive a car in 20 hours, like any 17-year-old. We would have machines. We would have domestic robots that can, clear the dinner table and fill out the dishwasher, and they could learn this in one shot, like any 10-year-old. We don't have any of this. What it tells you is that we're missing something really big in AI, and what we're missing, among other things, is the ability for AI systems to learn from the physical world, essentially interacting with the physical world. This is how we acquire common sense. And then we're missing other things like memory, reasoning, hierarchical planning, etc. So we need systems that learn world models, basically mental models of the world that would allow them to reason, to predict what the impact of their action on the world would be, so they can plan a sequence of actions to arrive at a particular objective. Systems that have persistent memory. We do this currently with RAG, Retrieval Augmented Generation, proposed by some of my colleagues from FAIR a few years ago. But it's really not completely satisfying. It'd be better to have like a separate system that can store episodic memory, systems that can plan action sequences, and systems that are controllable and safe, that are driven by objectives and not just by whatever training that we have. So what I'm proposing there is something I call objective-driven AI. And before I talk about this, I'm going to talk a bit about self-supervised learning. So self-supervised learning, of course, has taken over the world. I'm sure you've been hearing a lot about this today. For generating text, images, videos, 3D models, speech, even synthesizing, like designing proteins and things of that type. And the basic idea is very simple. You all know what it is. You take a piece of input, let's say a piece of text, you corrupt it in some way. The corruption generally is a sort of masking, but it could be something else. It could be a shift. It could be substitution of words, or it could be any kind of other corruption you might imagine. And then you train a very large neural net to basically reconstruct the parts of the input that are missing. And in the process, so it's an instance of something called a denoising autoencoder, which is a very old idea, actually older than Pascal Vincent's paper from 2008. There were ideas around this when I was doing my PhD thesis in the late 80s. But it's really kind of been demonstrated in a very impressive way by the self-supervised learning applied to text in the context of the BERT system, for example, from 2018. And the interesting thing there is that the bigger you make the network, the better it works, and the more the system seems to learn about the underlying nature and content of the text and the underlying reality to some extent. Okay, so that's a generative architecture. You're reproducing Y from X being a corrupted version of Y. And generative AI and autoregressive LLMs really are an application of this. So in autoregressive LLM, the particular architecture, of course, of the system is a transformer. And it's a transformer with what's called a causal attention, which means to predict a symbol, you can only look at past symbols. You can't look at future ones. That's done by masking the attention matrix. And so you train the system by once the system is trained, it can predict the next token that follows a particular piece of text. And it doesn't really predict a token. It predicts a distribution over tokens. So a token is a subword unit. Typically, there would be 30,000 different tokens in a typical language. Some models go to a few 100,000, but so 30,000 is, can be represented with 2 bytes. But what the system predicts really is a distribution over tokens, and then to produce a token, you sample from that distribution. So that produces 1 token, and then the autoregressive prediction process essentially shifts that output into the input. So now it's becoming part of the input, and now you predict the next token. Autoregressive prediction is not a new concept. It's been around in signal processing for decades. But in the context of language model, it's pretty amazing how it works with very large systems. So we all know that there is a whole bunch of those models around nowadays. They're trained typically on several tens of trillions of tokens. I'm not sure why my slide is out of date here. It's more like 10 trillion nowadays, if not more. And that's basically the totality of all publicly available text on the internet with some filtering. The number of parameters is typically between 1 billion and a trillion, more or less. And of course, there's a bunch of open models of this type for which you can just download the inference code, generally not the training code. Some of them going back quite a few years, like Blunderbot and Galactica from FAIR, and then more recently LLaMA, LLaMA 2, and CodeLaMA. Mistral from Mistral, and Mixtral, and then Mistral next. Falcon from the UAE, Alpaca from Stanford, Yi from 01.ai in China, Olmo from the Allen Institute of AI, and more just last week, Gemma from Google, which is a baby form of Gemini. And then there are proprietary ones, of course, Meta AI from Meta, which is built on top of LLaMA 2, Lambda, Bard, and Gemini from Google, ChatGPT from OpenAI, etc. Performance is really amazing, but they really made stupid mistakes. They make factual errors, logical errors. They are inconsistent. They have limited reasoning abilities. They can be toxic, and you can jailbreak them to kind of break away from their fine-tuning. They have no common sense, no memory, and they can't really plan their answer because they produce 1 token after the other. So you can download LLaMA, but I'm sure you know this already at this URL, or you can use it directly using a number of services that offer it either free or for for some money. And those things can answer any question you have. In fact, Meta AI is present in smart glasses that Meta sells, and you can talk to it and it can answer any question you have. It can even actually look at what you're looking and then tell you about what you're looking. Meta has something fun, which is fine-tuning a number of those Meta AI dialogue systems to play the role of experts in various things. So, for example, you can talk to Snoop Dogg, who's an expert dungeon master for Dungeon and Dragon playing. Other specialists of sport or fashion or whatever, science fiction, movies, etc. Now, generative AI, of course, also is for generating images, and that is making really fast progress. This is the EMU system from Meta, which has the advantage of being described in a paper. And you can use it through Messenger or WhatsApp by typing /imagine and then typing a prompt. So self-supervised learning really has had a big impact in natural language understanding, but also in translation. This is a recent project from some of my colleagues at Meta called Seamless M4T, and this is a system that can translate 100 languages in the input and produce 35 languages on the output. And it can do translation from text to text, text to speech, speech to text, and speech to speech, including for languages that are not written, like dialects. And there's a version of it that is real time with 2-second latency and preserves the voice and the expression of the speaker. If we had something like this in our smart glasses, this would basically erase a lot of language barriers, and would be the Babel fish, in Hitchhiker's Guide to the Galaxy. So this is a really impressive system. You can play with it. It's open to some extent. But okay, here are the issues with autoregressive LLMs. Every time an LLM produces a token, there is some probability that this token will take you outside of the set of proper answers. And if you assume those errors are independent, what that means is that the probability of staying within the set of good answers decreases exponentially as the answer kind of grows in length. And there are various studies about this by Yejin Choi at University of Washington, for example. So my prediction is that because of this and because of basically the impossibility of fixing hallucinations with autoregressive prediction, LLMs are doomed in a way. They're not going to last very long. We're going to replace them by something better. And one proposal is objective-driven AI, as I mentioned before, which I'll explain in a second. But I think there's too many things that are not fixable with the current paradigm that we're going to have to really make radical changes. Another thing that's interesting is people who, from cognitive science or kind of classical AI, if you want, who have studied the ability of LLMs to plan, and basically concluded that LLMs really cannot plan. They can produce a plan whenever the plan conforms to something they've seen in the training data, but they can't really invent a new plan. And that's really what planning is. And so there's a growing number of papers on this, particularly from Rao Kambampati at Arizona State University. He actually taught a tutorial about this just a few days ago at AAAI in Vancouver. And then there is another problem, which is, so this is a philosophy paper that I co-wrote with my colleague Jake Browning, who is a card-carrying philosopher. I'm not. And it says that really there is a limit to how much knowledge is contained in language. And if we only train AI systems with language, we're never going to get them to reach human-level intelligence because there's just not that much knowledge in language. This might sound surprising, but it's really true. So, autoregressive LLMs are good for writing assistants, for all kinds of things, very useful. There's a whole industry building around it, which, we should go. But in terms of a path towards human intelligence, they're really basically an off-ramp. We're easily fooled into thinking they are intelligent because of their fluency in manipulating language, but really they're not that smart. So that said, we have to kind of imagine what the long-term horizon is for AI research. And really, there's no question that at some point in the future, probably not very far in the future, certainly in your lifetime, if not in mine, we will have machines that surpass human intelligence in all domains. And this will increase humanity's total intelligence, if you want, right? It will amplify human intelligence. And we should certainly welcome this, not fear it, because intelligence is really the commodity that is most in demand in the world. But again, to do this, we really need systems that really understand how the world works. And this is not just understanding how the world works like humans do, even like cats and dogs. Cats and dogs can do amazing feats. They understand the world much better than any LLM. And to some extent, they have actually more knowledge than LLM. So how do we get to that level? Before we get to human intelligence, maybe we can get to cat level intelligence. And here's an interesting remark, I think. A typical LLM is trained with 10 trillion tokens, right? So that's 1 10 to the 13 tokens. Each token is 2 bytes. So we're talking about 2 times 10 to the 13 bytes of training data. This is text, so it would take you and me reading 8 hours a day at 250 words per minute. It would take us 170,000 years just to read this, right? So certainly computers can read this much faster than we can. LLMs can digest this data much faster than we can. And perhaps we can conclude that they will accumulate a huge amount of knowledge and be smarter than us. But in fact, that reasoning is false, because let's talk about a human child. A human child, a 4-year-old, has been awake 16,000 hours, which, by the way, is a small amount of video. It's about 30 minutes of YouTube uploads. We have 2 million optical nerve fibers going from our eyes to our brain. Each fiber carries about 10 bytes per second, roughly. Probably a lot less, so that's an upper bound. So the data volume that a 4-year-old has seen during his or her life is 10 to the 15 bytes. That's 50 times more than the biggest LLM. Okay, so this is very redundant data. But redundant data is exactly what we need for self-supervised learning to work. Self-supervised learning learns from the redundancy in the data. It learns the structure of the data you feed it with. And that's really better if you have more redundancy in the data. So in 300 hours, a child has seen more data than an LLM through vision. So that tells you something about text and language. Text is very low bandwidth. Sensory input is much better. So the only way we'll ever get to human level intelligence, or even to animal level intelligence, is if we get systems to learn from sensory inputs like vision, or high bandwidth sensory input, regardless of what it is. We're not going to get there just with text. We're already exhausting the amount of text that is being used, right? It's the entire supply of text publicly available on the internet already. We see saturation in language models already. Okay, so how do we do this? So 2 things. I'm going to first talk about the objective-driven AI architecture, and then talk about the central piece of it, which is world models. And there's a paper that I wrote, I put it online in June 2022. You see the URL here. A path towards autonomous machine intelligence. And there's various versions of the talk I'm giving you right now online if you want to look at it again or have a different view of the same topic. So here's the idea. The idea is to build a system that has multiple modules which are trained simultaneously. And whenever you have an arrow between 2 modules, it means that the module can send data to another module, but also that gradients can be backpropagated through that arrow backwards. Okay, so I'm assuming everything there is differentiable, and we can propagate gradients. The cost function computes a scalar value, which is a cost, and it can backpropagate gradients to the world model, to the actors, to the perception system, to basically train them. Think of the cost here as a cost function, but also an objective function for training. Okay, let me describe an episode for that objective-driven AI system. And it's very simple, and it's very much inspired by very classic work in optimal control. So you observe the world through sensory input. That goes into a perception module, let's say a ConvNet or a transformer, whatever it is. And that system gives you an estimate of the initial state of the world coming from the observation. Now, of course, we know a lot more about the world than what we currently perceive because we have memory. So maybe you will need to combine your current perception or representation of your perception with the content of a memory that tells you things that you observed in the past that are still true. Okay, so the combination of those two things gives you an idea of the current state of the world. You plug that into a world model, and this is really the centerpiece of the whole architecture. And the other thing you feed to the world model is an imagined sequence of actions that you might want to take. Okay, so imagine a sequence of actions, feed it to your world model, and from the initial state of the world model predicts what the resulting state of the world will be after you've taken the sequence of actions. Now, this may not be a single prediction. It could be multiple predictions because the world is not entirely predictable or deterministic. But let's ignore this for a moment. So you get a prediction that is the result, the outcome of taking this sequence of actions. And then you feed this to two sets of objectives. One that measures to what extent the system is satisfying the task, okay, to what extent the task has been accomplished. And another set of objectives that basically are guardrails, right? So a guardrail would be, okay, this is a domestic robot, and you just ask the system through the task objective to fetch you coffee, and the system tries to get to the coffee machine, but your best friend is in the way, and the robot cannot get to the coffee machine. The guardrail says, just wait for the person to get out of the way, or ask nicely for the person to get out of the way. Don't run that person over. Okay, so this is the kind of guardrails that we're talking about here. And then the way the system operates is that through optimization, it tries to find a sequence of actions that will minimize those objectives. Think of those objectives as functions that have a scalar output, okay, and you compute the sum of them. And so that's like a cost function. And we're going to use this cost function not to train the system, but to do inference, right? We're going to infer the value of those variables, the action sequence, by minimizing those things at runtime. Okay, we're not talking about learning yet. So basically figure out an optimal sequence of actions so that the resulting state of the world will minimize the objectives, accomplishing the task while not causing any major damage, essentially. Okay? Now, of course, it's pretty clear that your world model will have to be perhaps applied multiple times. Let's imagine that your world model is actually something that gives you the state of the world at time t+1, given the state of the world at time t and a single action you're taking. Then you might need to run your world model multiple time steps. Here, 2 time steps, right? So take action 0, you get a predicted state. Take action 1, you get another predicted state, the final state. Measure the cost, whether the task has been accomplished, and the guardrail costs are measured over the entire trajectory. This is very similar to a process, classical process in robotics and optimal control called model predictive control, MPC. The way you perform this optimization with respect to the action can be gradient based. So you can backpropagate gradient through the world model from the cost through the world model all the way to the action and do gradient descent. Or if the actions are discrete or the world model or some of the costs are not differentiable, you could use things like graph search or dynamic programming or A-star, Monte Carlo tree search, other things. But it's very likely that gradient-based optimization methods are much more efficient for this. As is the case for training neural nets. It's more efficient to use gradient-based methods, backprop, than to do random search, right? So to handle the non-deterministic nature of the environment of the world, you may have to have extra input to the world model that are latent variables. So latent variable represents everything about the state of the world that you don't know, which basically prevent you from making accurate predictions about what the next state is going to be. Those latent variables need to be either sampled from a distribution or maybe swiped over a set. And then the planning has to be done in the presence of those latent variables, which is not simple and not completely worked out, although there's quite a bit of work on this kind of problem. But you have to deal with that. So basically, viewing the probabilistic nature of the computation here as being a separate process that basically is a set of latent variable that you feed to a set of deterministic functions. Neural nets are deterministic functions. So those symbols here are deterministic functions. Those symbols, the squares, are scalar valued cost function. The round shapes are variables, some of them being observed, some of them being inferred. Okay, what we really want to do ultimately is hierarchical planning, because if I want to go from, say, New York to Marrakesh, I can't plan the entire trajectory of me in terms of millisecond by millisecond muscle control. What I do is I do hierarchical planning. So here's an example. Let's say I'm in office at NYU and I want to go to Paris. So my objective, task objective is my distance to Paris, basically, right? 0 if I'm in Paris, a large number if I'm not. So obviously I should decompose this into two actions. One of them is go to the airport, and the second one is catch a plane. Okay, and there might be some latent variables here, which are things I may decide or that the environment may decide for me, which I may not control. Okay, so first action, go to the airport. Second one, catch a plane. Now my state here represents whether I'm at the airport or not, and so I can measure my distance to the airport by basically, measuring to what extent a lower level planner will get me to that state that specify whether I'm at the airport or not. So now how do I get to the airport? Well, I'm in New York, so I need to get down on the street and hail a taxi. Okay, that's my two actions. How do I get down in the street? I need to go to the elevator, take the elevator down, walk out the street. How do I get to the elevator? I need to stand up from my chair, open the door of my office, get out of my office, press the button of the elevator. How do I get up from my chair, etc.? So you can imagine there is a whole hierarchy of actions of this type, multi-level, all the way down, where the lower level is actual actions I can take in the world, like controlling my muscles, right? And that needs to be planned for a very short time in terms of milliseconds, but I cannot plan the entire trip to Paris in terms of the lowest level. I need the planning to be hierarchical. Okay, so hierarchical planning is a very important thing to be able to do if you want an intelligent system to accomplish complicated tasks and plan those tasks. We have absolutely no idea how to do this other than this very vague idea that I'm presenting here. There is basically no technique that has been demonstrated that can do hierarchical planning where the level in the hierarchy are learned. Okay, what is necessary for this is a system that can learn multiple level of an abstraction, hierarchical representations of increasing level of abstractions. Okay, so when I make predictions in terms of low-level muscle control, my level of abstraction of representation of the world here is very low. My predictions only need to go a very short time in the future. On the other hand, if I'm predicting in terms of going to the elevator or something like this, I can make some relatively accurate prediction to within a minute or something like that. At a high level of abstraction where I don't take into account all the details, but I know I can get to the elevator within a few seconds, right? And then at a very high level of abstraction where, this is going to the airport and catching a plane, I can say that, within 10, 12 hours, I'll be in Paris, but I can't tell you the details, right? So I can make plans at a high level of abstraction by making prediction very long in the future. And if I make predictions at a short term in the future, then I need to make those predictions at a low level, and vice versa, right? So how to train a system like this so that it can do planning at multiple levels, that's a big open question, essentially. A good topic of a PhD if you want to get into a PhD program. Okay, so how can we learn world models from sensory inputs? So baby humans and animals learn how the world works in the first few months of life by basically observing the world initially and then interacting in the world, moving things and experimenting. But initially, it's mostly just observation. So we learn, basic things like the difference between animate and inanimate objects, the notion of object permanence, and the learning of natural categories before we can give names to them, stability and support, and things like gravity and inertia and intuitive physics. That comes around 9 months. So before 9 months, babies don't really understand gravity. You can show them objects that appear to float in the air, and they're not surprised. Whereas after 9 months, they get surprised, like the little girl here at the bottom. If you show them a scenario where a toy is pushed off a platform and appears to float in the air, they've learned about gravity. So what kind of learning takes place there? And so basically it's the question of how do we learn a world model? And of course, there's a natural idea, which is to use this idea of generative AI, right? We can learn to predict what's going to happen in a video, and so the same way that we do it for text, instead of corrupting a piece of text, we corrupt a piece of video. Take a video, corrupt it in some way. For example, mask the second half of that video, and encode perhaps an action that is being taken in that video or not. So anyway, corrupt or mask that video, or take an action, or encode an action that happens in that video, and then run that video through a generative architecture that tries to reconstruct what's missing in the video. And this basically doesn't work. And we've been trying to get things like this to work for almost 10 years now. We have a paper going back to 2014 to use video prediction to basically pre-train a computer vision system to extract good features from video, and it basically doesn't work. Now, we have systems now that can, of course, synthesize video, and they look nice, but that does not mean that the representations that they learn are useful for downstream tasks like predicting what's going to happen, or in a useful way, or representing images in such a way that the representations can be used for a subsequent task, such as object recognition or segmentation or action recognition in video. So I tell you, generative architectures for images and video do not work. They do not work well. Not if you want to use them to learn representations of the world. Of course, if you're interested in generating video, of course, you have to do that, but not for representing video. And the main issue is that the world is somewhat unpredictable, and so if you train a big neural net to make a single prediction for what's going to happen in the video, it makes a blurry prediction. You see an example here on the top left. There are other examples down, but I'm not going to explain. And the reason is because there's many plausible things that could happen, and among the many plausible things that could happen, the system just predicts the average of all those things, and that's a blurry prediction. So you can, to some extent, solve that problem using latent variables like GANs. So this paper from 2016 actually used GANs. So basically latent variable models to try to solve that problem. And we tried to do this for many years, since 2015, and basically failed, more or less. I mean, they kind of work, but not really well. People have tried to use diffusion models as well. This is still ongoing, not clear where that's going. People have tried to use denoising autoencoder. It really doesn't work that well. So my solution is what I call joint embedding architectures, and particularly something called a joint embedding predictive architecture, or JEPA. And we've had a number of papers on this going back a couple of years. So the difference between a JEPA and a generative architecture is that you also run Y through an encoder. Okay? So in a generative architecture, you don't have this encoder. This encoder here is the identity function. Okay? So if you don't have an encoder here, then what the system needs to predict is all the pixels of the video. But if you do have an encoder, what the system needs to predict is just a representation of that video. And in that representation, it's quite possible that the encoder will eliminate a lot of information that is very difficult to predict, or impossible to predict because you just don't have enough information. So that's the basic idea of joint embedding. Why joint embedding? Because you take both Y and X and you embed both, okay, into the space of Sx and Sy. And then you make predictions in that space of Sx and Sy. Okay, but otherwise the principle is the same. Take Y, apply a transformation, a corruption, or an action that produces X, and then make a prediction from this corrupted X. But the prediction you're trying to make is a prediction of the representation of the full input Y. Okay. So that's joint embedding predictive architecture. So that's the difference between generative and joint embedding. And again, you could think of generative as being a special case where the encoder of Y is the identity function. Now, the advantage of joint embedding is it basically lifts the representation level of what you're trying to do here. It learns to extract a representation of the input such that within the representation space, predictions can be made accurately. Okay, so it's going to eliminate all the stuff that is not predictable, which you can think of as noise, essentially. It's going to eliminate all kinds of details about the input that really could not be predictable. Okay, and it basically constructs an abstract representation within which those predictions can be made, and perhaps that's the element, the basic element we need for those kind of hierarchical world models. If you think about this, if you have an action variable going into the predictor, this is very much a world model, right? Give it a perception, it extracts an idea of the state of the world, and then using an action, it predicts what the next state of the world is going to be. And you can use this to, multiple times with a sequence of actions. That's what we need for a world model. So there's several flavors of this, and some of them go back a very long time. The basic idea of joint embedding architecture actually goes back to Siamese networks back in the early 90s, and then a bunch of papers in the early 2020s. Pearl, Moko, Seam-Clear, Barlow Twins, Vikreg, etc. Then we add a predictor, which doesn't have latent variable or action variable that's things like BYOL from DeepMind, Vikreg, L from my group at Meta, and IJPA, which I'll talk about in a minute. And then the full-fledged version with latent variable, this would be Equerry and Vikreg and IJPA, which I'm not going to have much time to talk about. Okay, so that's the JEPA architecture, and I think this is the future of AI and world modeling. If we want to get to systems that understand the world, I think we have no choice but use this kind of architecture. To train those architectures, we're going to need to train them to minimize the prediction error here, but we're going to train them all at the same time. So training the encoder and the predictor simultaneously. And perhaps training also the system that produces the distribution on Z. And we may need to have extra objective functions, the C of SY, that basically drive the system towards learning types that represents and not others. So basically, that can be used to bias the system towards learning certain things. So to kind of understand how this works, I have to explain the concept of energy-based model really briefly, because with this kind of model, you can't really use probabilistic modeling to say, oh, this system, estimates the P of Y given X. It doesn't, because it does not actually predict Y. It predicts SY. And it's not really probabilistic unless you put a distribution on Z. And so the best way to understand this is through what's called an energy-based model. So imagine we have two variables, X and Y, and we want to capture the dependency between X and Y. So certain X, given an X, there are certain values of Y that are compatible with X. So for example, in the context of video, if X could be the initial segment of a video and Y a proposal for the continuation of that video. And what this function should do is produce a single scalar value that is small, let's say 0, if Y is a good continuation for X, and large if Y is not a good continuation of X. Okay, so in the case of a scalar situation like this, where X and Y are scalar, let's imagine our data points are those black dots. Okay, then what we want is this energy function, f of xy, to represent the dependency between X and Y by giving low energy to the black dot and regions around them, and then higher energy to other regions outside of the manifold of high data density. So think of this as the level set or the lines of equal cost of the energy landscape, right? So the energy function is used for inference. It's not used for training. The purpose of training is going to be to shape this energy function so that it gives low energy to stuff we observe and high energy to stuff we don't observe. To do this, there are two classes of methods, contrastive methods and regularized methods. And we have to use this because if we only pull down the energy. So if you only change the parameters of our energy function so that the training samples have low energy, then we run the risk that the entire energy function will be zero, like it will basically be flat, right? So this is the collapse problem that we observe here. This is a particular very simple neural net that we train to just give low energy to the blue dots, and it does that by giving low energy to everything. That's not useful because that does not capture the dependency between X and Y. So a simple fix to this is what's called contrastive methods, and contrastive methods consist in generating a bunch of those green dots here that are outside the manifold of data. You can do this by basically corrupting the blue dots, if you want. And then you push their energy up. And if you think about what a denosing autoencoder does, that's exactly what it does. Denosing autoencoders and contrastive methods for joint embedding architectures like Siamese nets, like SimClear, for example, they do exactly that. You have positive pairs and negative pairs. Positive pairs, you try to make the distance between representations as small as possible. Negative pairs, you try to push them away. So you try to make the energy large. So that's contrastive methods. The problem with contrastive method is that they kind of break down in high dimension. So it's a representation space in which you work is high dimension. You need a lot of negative contrastive samples to get the energy surface to take the right shape. And so I've become fairly pessimistic about this, even though I've kind of one of the original papers on it in the 1993 on Siamese nets. I became much more positive about those regularized methods. And the way those methods work is by basically minimizing the volume of space that can take low energy. So that if you push down the energy of certain regions, the other regions have to go up in energy because there is only a small amount of volume that is allowed to take low energy. So that are those two methods. I really prefer regularized methods now, although we have papers that show that there is a duality between those two methods, and at some level they should be equivalent, but in practice I really prefer the regularized method. I may be right or wrong. Okay, so far I've told you a number of different things. First thing is abandon generative models in favor of joint embedding architectures. This is a winter school on generative models, and I'm telling you, forget about generative models. I mean, don't forget about them if you are interested in generating, but forget about them if you're interested in really building AI systems. Abandon probabilistic modeling in favor of those energy-based models, which is, I think, a much better sort of intellectual framework for it. Abandon contrastive methods in favor of those regularized methods. And of course, as I've said for many years, don't even think about using reinforcement learning, except for really kind of fine-tuning systems because it's so inefficient. So how are we going to train those joint embedding predictive architectures? And there's basically there's two classes of non-contrastive methods. One class that works by maximizing some measure of information content coming out of the encoder to prevent collapse. Okay, so this has the effect of actually minimizing the volume of space that can take low energy if you maximize the information content coming out of the encoder, while at the same time minimizing the prediction error. So you train everything all at once, train the encoder to carry as much information as possible from the input, and train the predictor to predict as much as it can from the representation of the representation as well. And so the system will try to find a trade-off between carrying as much information as possible, but not carrying information that is not predictable, right? And that's really what is interesting about this. This other thing here I'm not going to talk about. If you have a latent variable, you also need to minimize its information content. But let me not talk about this for now. So one particular method that I like is called VICREG. That means variance, invariance, covariance regularization. And the basic idea here is to prevent a collapse. A collapse here is manifested by the fact that the encoder completely ignores X and produces a constant vector. Same for Y. And now the job of the predictor is trivial, right? Because it's just a constant Sx and Sy. But the system doesn't do anything. So it gives zero energy to everything, right? So to prevent that from happening, the first thing you can do is make sure the components of the Sx variable are not constant, that they vary over a batch, let's say, right? So take a batch, measure the standard deviation of one component of Sx over this batch, and plug this to a cost function, in this case a hinge loss, that make sure the standard deviation is larger than 1, okay? And do this for every component, and do this both for Sx and Sy. So that will prevent the system from completely collapsing and having constant outputs. But it could be that the Sx will be all very dependent of each other, correlated, or maybe even equal. So to prevent that from happening, add another term here, and that term basically tries to decorrelate the components of Sx. The collection of those two terms basically tries to make the covariance matrix of Sx computed over a batch to be as close as possible to the identity matrix. Okay, variance 1 on the diagonal, covariance 0 off diagonal. There's a very similar method proposed by LLaMA at Berkeley called NCR squared, deriving from slightly different arguments, but very similar. Now, it turns out this is not completely sufficient because you only get variables that are uncorrelated but not independent. So a way to mitigate that problem is to run the representation vector into an expander that expands the dimension. So Vx is really a higher dimensional vector than Sx. And within this space, you do this variance covariance regularization. And we have some papers that show that this actually has the effect of making the components of Sx more independent of each other. Not completely independent, but at least pairwise independent in certain conditions. This is the paper I'm talking about here. This may have some interesting applications in source separation and ICA, by the way. Okay, so then once we've trained the system, what we're going to do is take the representations here and feed them to a classifier and see, train this classifier in supervised mode and see what performance we get on, say, object recognition or something like that. And so this is like a whole bunch of self-supervised methods, some of which are contrastive, some of which are non-contrastive, of the type that I'm talking about, like Barlow-Twin and Bickreg. And the performance that they yield on ImageNet after pre-training on ImageNet with data augmentation, with various distortion of images. So this is in the kind of the top, the pack top performing. This works pretty well also on sort of transfer tasks for Pascal VOC, INAT. So these are fine-grained classification. Also for detection, although not super great for detection. For detection, we have a modification of Bickreg called Bickreg-L for local that actually learns kind of local features and then does some matching local features. This works really well for detection, segmentation, things of that type. But here is another family of methods that are called distillation. And these have the advantage that they have advantages and disadvantages, and you can put BYOL from DeepMind in the same category, SimSiam, DinoV2 in this category, as well as IJPA, which I'm going to talk about next. And the way this works is that you, again, have two encoders, but they have to share the same weights, except they don't have exactly the same weight. The encoder of Y uses weights that are basically exponential moving average of the weights of the encoder X. And then you cut the gradient. You don't backpropagate gradient through the encoder of Y. You only backpropagate gradient through the predictor and the encoder of X. Now, for some reason, if you do this properly and you have proper normalization everywhere, this does not collapse. I can't tell you why it doesn't collapse, but it doesn't collapse. So it's a bit strange that we don't have a full understanding of why it doesn't collapse. There's a number of papers on this. I'm not sure I believe all of them completely. So, but it works really well, and it's really efficient, and it's fast, and this variant of it. One variant is DinoV2, and this one actually, in this one, the representation here is quantized. So it's basically a classification problem. So Sy is basically the output of a softmax. So you have categories, very large number, and you train the encoder and the predictor to kind of match the distribution over those virtual categories. It's completely unsupervised. So DinoV2 really works really well if you want a self-contained image feature extraction that is completely generic and works well for all kinds of applications. You probably should use DinoV2 at the moment because it's, among all the methods that I talked about, it's the one that's been trained with the largest data set. It's not necessarily the best method, but it's the one that works best at the moment because we trained it and fine-tuned it really well. So this is from Okab et al. At Fair Paris. And you can just download it, play with it and download it here. And it can be used for all kinds of stuff, extracting features. This is a visualization of what features are being extracted from natural images, but also for object recognition. I'm not going to bore you with detail, but this works really well for things like recognition of objects in things like ImageNet and things like that. Extracting features from video, extracting depth, so you can train ahead to extract depth, to do segmentation. I mean, it's really, really very generic, and it's amazing the way it works. Some of our colleagues at Fair Paris have used this to build a system that extracts an estimate of the height of the canopy in forests. They've trained it with a relatively small amount of data where we have LiDAR images, so we know exactly what the height of the canopy is. And then you train ahead on top of the V2 features. Then you can apply this to the entire world from satellite images with sub-meter resolution. And what you get now is an estimate of the total amount of captured carbon inside of vegetation, which is a very important quantity to know about. But let me tell you about another example of those distillation architecture or distillation systems. This is a paper that appeared about a year ago called ImageJEPA. And the idea there is you take an image, you partially mask it, you feed it to transformers, and again, there is this exponential moving average weight sharing between them. And then you train a predictor to predict the missing pieces, basically the features that are missing from the input. You try to train this entire system to kind of predict those. And this runs really fast. So this is the number of GPU hours here on the x-axis and the top 1% performance on ImageNet compared to other methods that are based on reconstruction or based on supervised learning using text. In fact, here is a better version of it. So the square here represent some work by our colleagues in Menlo Park called MAE, Masked Autoencoder. So this is a generative architecture, basically a denoising autoencoder for images. And what you can see is, for the same kind of architecture, you get better performance out of IJEPA, and you get it faster also with fewer training. And you don't need any data augmentation. It's just masking. It's the same for MAE. It works, just about as well if you compare it to, other methods like SimClearDino and ibot in the same conditions, which means, and those methods require data augmentation, which IJEPA, MAE, and Data2Vec do not require. So it's really great. You get good performance also on sort of the low data regime where you only train supervised on 1% of ImageNet. You can still get something like 77% or so. But the more recent work is a video version of this, VideoJEPA. And there is a blog post, a paper, and code that you can download and demos. So this is the paper. I think it's on archive now. I'm not entirely sure, but in any case, you can get it from here. And it's the same idea as IJEPA. You take a video, 16 frames in our case, corrupt it by masking it. And what we do is mask a tube over time. So it's the same regions of all the frames that are masked. Run both through encoders using exponential moving average weight sharing. And then encode the position of the mask using positional encoding, and encode the position of the places that need to be predicted, and then feed that to a predictor, which is a big transformer. And train the predictor to predict the representation. And again, there is a cut gradient here because of the EMA weight sharing. So this paper is just came out a couple of weeks ago. And this works really well for learning features to classify videos. Okay, so this is the performance on two datasets, Kinetic 400, which is actually relatively easy, and something V2, which is quite a bit harder. And those are kind of self-supervised system that are either using pixel prediction, so basically generative model, OmniMAE, Video MAE. And the triangles are also SSL systems, but they are trained on frame by frame. So they're not trained on video, they're trained on images. That includes IJPA. And then there's OpenClip, which is trained using text, so it's not really self-supervised. And you see that VJPA really beats pretty much all of them, particularly on something v2. Kinetic is different. Dino v2 actually is slightly better because for Kinetics 400, you don't need to actually watch the video. Just one frame is enough to tell what it is. And so an image model actually works okay. But something you really need to watch the action to be able to tell what it is, and then the performance is much better, like 20% better. I don't want to bore you with details, particularly because I'm getting close to being out of time, but the results are really good. You can look up the papers, and it's pretty fast to train also. And it can you can train a decoder post hoc, right? After you train the JPA architecture, you can take the representation and train a decoder to produce a representation of the image that is hallucinated, right, in the blanks, and it makes predictions that are reasonable. Like this is a video of someone cooking, and it continues the cutting board and whatever it is that the person is cooking, etc. Okay, so I'm coming towards the end. We still have a lot of problems to solve to make this work in terms of a complete agent according to the architecture, objective-driven architecture I showed you earlier. JPA with regularized latent variable, planning algorithms in the presence of uncertainty, learning cross modules for particular tasks, planning with inaccurate world models, as well as expression to as a world model in cases where the world model is not completely accurate. So we're working on SSL from video, as I showed you, LLMs that can reason and plan and are driven by objectives. And this is what eventually will result from this work, as well as a system that possibly can do hierarchical planning. Let's see. Okay, so we need more computing power. It's necessary, but not sufficient. We're not going to get to human level AI by just scaling up current architectures that we have. It's just not going to work. And what we get out of the objective-driven AI is we get systems that can plan their answer, right? They don't just spit out one word after the other without thinking in advance. They plan their answer, and then they turn their answer into text or into action sequences. But there is some thinking, right? So the system basically is capable of spending an unbounded amount of time thinking about a problem before putting out a solution. It's not the case for autoregressive LLM. Autoregressive LLMs spend a fixed amount of computation per token produced. So that's not really Turing complete, unless you corner the system into producing a lot of tokens, which is what chain of thought does, but there's limits to what can be done. So I presented perhaps some of the essential concepts that we might be missing to reach human level AI, but there is still a lot of work to do. I mean, this is basically a 10 years program. Eventually all of our interaction with the digital world will be mediated by AI assistants, which means that AI assistants will constitute a repository of all human knowledge and culture and languages and value systems and centers of interest. And so this will constitute a shared infrastructure like the internet is today. And the main conclusion to this is that those platforms must be open source. They must be open, because we cannot have a small number of AI assistants controlling the entire digital diet of every citizen across the world. This would be extremely dangerous for diversity of thought, for democracy, for just about everything, right? So what we need is not one AI assistant. We need base models, and we don't need 50 of them. We just need a few things like LLaMA 2, like Mistral, like Gemma, like etc. A few base systems that are then fine-tuned, and they can be fine-tuned by anybody. They should be able to be, anyone in the room here should be able to get together and fine-tune that system so that it speaks, Arabic, and it understands the culture of Morocco and knows everything about Marrakesh. So we need those platforms to be open because we need a high diversity of AI assistants. For the same time, we need high diversity of the press, so that we have a diversity of opinion and a high diversity of sources of information, because no one has, the absolute truth. So what's important now is that a lot of governments are thinking about the benefits and the dangers of AI, and some of them are thinking that AI is too dangerous to put in the hands of everyone, and they're trying to regulate it and basically make open source AI illegal, regulate it out of existence. I think that's extremely dangerous. It's very dangerous for the future of humanity even. So there are people who think AI is too dangerous and should be regulated, and there are people like me who think it's too dangerous to have AI controlled by a small number of people, because those AI platforms will control what everybody sees. And so that needs to be open, like the open internet, right? This is the collision of technology and politics, if you want. It's going to take a long time before we reach human level AI. It's not as simple as people make it sound. And before that, we're going to get to things like cat level or dog level AI. There is no such thing as AGI, artificial general intelligence. The reason that there is no such thing is because even human intelligence is very specialized. We are very specialized. We think we have general intelligence, but we don't. And intelligence is not just a linear measure. You can't measure it with a scalar. It's a collection of skills and an ability to learn new skills quickly. And some animals are smarter than we are in certain tasks. It's just not unidimensional. But there is no question that machines will eventually surpass human intelligence in all the domains where humans are smart. We should see this as actually a big benefit. AI will amplify human intelligence and will bring basically a new era of enlightenment to humanity, a new renaissance perhaps for humanity, the way the printing press did the same thing in the 15th century Europe. And we need to take advantage of this, prepare for it as well. Thank you very much.
Thanks a lot. So perhaps so we can take some questions. So do you hear us, Yann?
Yep.
It's okay? Okay. So
I hear you fine.
Who have questions?
Thank you very much for this impressive talk with so much vision. At some point, you mentioned that, among others, we should abandon reinforcement learning in the near future. Is it possible that you elaborate on that, since reinforcement learning is heavily used somehow in LLMs?
Well, so the type of reinforcement learning that is used in LLM, which is RLHF, is not really reinforcement learning. It's really learning an objective function, right? So it's basically, take the internal state of the system or the answer and feed it to an objective function, and then train that objective function to predict what a person would say. So it's a very kind of, how would I say, stripped down version of reinforcement learning. It's the equivalent of, learning a value function or maybe even a critic. But it doesn't have all the exploration. There's a lot of aspects of reinforcement learning that really are not present in RLHF. And what people are doing now are things that actually don't do RLHF at all, right? They're more akin to supervised learning than to RL. Okay, so there's one thing that I think one distinction that needs to be done, which is that in the difference really between what people call, between supervised learning and what people call reinforcement learning is whether the cost function is differentiable or not, right? So in supervised learning, your cost function is differentiable. You give the correct answer, you can compute the cost of the answer, and you can backpropagate gradients so that your answer gets closer to the one you want, okay? But in fact, you can imagine all kinds of scenarios that are not supervised learning where the cost function is differentiable. Now, in what most people mean by reinforcement learning is a situation where there's two aspects to it, but one aspect to it is that the cost that you're minimizing during training is not differentiable. And so the only way you can train the system is by perturbing the output to figure out which one is best, and then getting the value of the cost function by perturbation, right? So this is gradient-free optimization, basically. Okay, and one way to solve that problem is to basically train a differentiable function that approximates that function. And that's the most efficient thing you can do. That's what the actual critic methods do in RL. The critic basically is that function that approximates a differentiable approximation of the value function, or a discounted future estimate of the value function. So, I'm not saying we should completely abandon RL. What I'm saying is that we should minimize its use as much as possible, because it's very inefficient in terms of sample efficiency, right? Particularly in real scenarios where you have an action and then you wait for a reward. That kind of scenario is just so horribly inefficient that it only applies to simulated environments, essentially.
Yeah, I have another question. So it's related to LLMs, and I'm curious about what is the modules that we need to focus on in order to build some LLMs with less parameters, but with a good quality. Yeah.
So I can answer that question, because I think you see progress almost weekly on this. The people who come up with new architectures with fewer parameters that turn out to work as well as bigger ones. So we've seen this with Mistral, for example. So Mistral has a good trick, which is it uses local attention circuit, right? The various stages in the system don't look at the entire input. They look at only kind of a local neighborhood in the input, a little bit like convolutions. And that has the effect of reducing the number of parameters, increasing the speed of performance, and the speed of inference, essentially, for the same number of parameters. So you can have a effectively bigger model that can do more computation with the same number of parameters than you had before, which is a good thing. And you keep seeing ideas of this type popping up like all the time. So I'm not going to make predictions, but I think I can tell you a little bit where I think the future of LLM is. And I think the future of LLM will be systems that can basically do what I described in the talk. So systems that build a representation of the question, then compute a representation of the answer using a predictor, very much like in the JEPA architecture, right? Then do some inference with some sort of world model. And then the world model there is basically the idea that the LLM has of the state of mind of the person it's talking to. When I talk to someone, I talk to you at the moment, to the audience, I have some idea of what the audience knows and doesn't know. And what I say is what I think something that will be useful to them, right? Will bring them to kind of a new state of mind. They know something that they didn't know before in terms that they can understand, right? So I think that's the way dialogue systems should work. They should have some mental model of the person they're talking to, and then plan their answer as a function of that to satisfy a certain goal. And then do this at the representation level, abstract representation level, not in terms of text. And then finally turn this abstract representation of the thought of the answer into text. And that can use autoregressive prediction, because that's what autoregressive prediction does well, producing fluent text. But it has to be conditioned on an idea, basically, which is a representation of what you want to say. If you were to ask me that question in French, my internal mental representation of the answer would be exactly the same as the one I currently have answering in English, right? The underlying thought of the answer is the same in French and English. And so what that means is that I'm not producing my answer autoregressively by just producing a word and then continuing. I'm thinking about what I'm going to say. I have an abstract representation of what I'm going to say, and then I turn it into text. And whether it's English or French doesn't matter, right? So that's, I think, where the future architecture of LLMs is going to be.
Thank you for your intriguing talk. For it to be a world model, there should be data infrastructure which would contain all of the information contained in the world, but not only one, a lot of copies to make simulations. Do you think this is achievable, and if so, how much time would it take for humanity to reach that level of technology?
Yeah, that's a good question. There's an aspect of the model I propose here, which I didn't talk about. And in the first slide where I show the architecture, there's a module at the top in blue called the configurator. The role of this configurator is basically to configure the world model for the situation at hand. So that configurator can, for example, if the situation the system is facing is driving, you have one world model you're using. Or if it's a domestic robot and it's cooking, it's another world model. If it's clearing up the table and filling up the dishwasher, it's yet another world model. But all of those world models have something in common. They deal with the real physical world. And so instead of having three completely separate models with some sort of mixture of experts to decide what to do there, you basically have one world model, but it's configurable through this configurator for the situation at hand. And there is some evidence, perhaps, that this is the way the brain of humans and lots of animals is organized. And the best evidence for this is the fact that we can only do one conscious task at any one time, right? If we think about solving a particular task, like building something or cooking or whatever, we can only do one such task at any one time. We can do lots of subconscious tasks simultaneously. But if we need to be deliberate about it and plan or what we're going to do, we can only do one. That seems to suggest we only have one engine that allows us to do this prediction. We have one engine that can do world models. And that engine needs to be configured for the situation at hand. So that's what I put in that model.
Okay, so last question, and then we will thank Yann. So last question.
When we're talking about this sort of word model, do you think the attention mechanism is powerful enough or efficient enough to actually capture the state of the word in the form that you're talking about? Or do you think we need to find a different sort of mechanism to actually do this?
Oh, I think there is a need for very wide exploration of architectures to do this, right? I mean, basically, we have a relatively small number of basic architectural components that people use over and over again nowadays. One of them is, convolution and pooling. And when I say convolution, I mean that like in more general term, which means local operations that are repeated across locations, okay? That has the advantage of being equivariant to shift, so that if you shift the input, the output is also shifted, but otherwise unchanged. Now, transformer blocks have another property, which is that they are equivariant to permutation, right? Permute the inputs, and the output are permuted, but otherwise unchanged. That's a very interesting property as well, particularly when what you're trying to do is a function that really depends on the relationship between objects and not strictly on where the objects appear, okay? And to some extent, that subsumes convolution, but in a very inefficient way. So what I think is that the future of video systems, for example, will use convolutions in the first few layers. They'll have to, because transformers are just too inefficient, right? It's order n squared in terms of complexity in the number of tokens, so it just doesn't scale. And so we're going to have to use convolutions at the low level. And in fact, that's pretty much what the brain does. I mean, the visual cortex and the auditory cortex are locally connected with neurons that basically are repeated over space. And then at a higher level, when the representation starts to be more object-based, then it makes sense to use things like self-attention. But I think, we need to invent new components of this type. Like, self-attention is not the end of, is not the be-all, end-all. It's not the panacea. I think there is a space for a lot of exploration there.
Thanks a lot, Yann, again for your participation. So we will